Yeah, so with our electronic challenges here today, it's a pleasure to welcome Michael Glinsky, many of whom, at least in the plasma physics world at the lab, know him. He has a 30-year career focused on data science, deep learning, Bayesian data analysis, which is going to be very popular with our crew, I guarantee. Worked in laboratories like ours, but also companies like Royal Dutch Shell, BHP, Halliburton, the list goes on, LL&L, Sandia, faculty member in the physics department of Western Australia. Again, going back to some of our laser interaction community here, was a key member of the team that founded Invasics, an NEA lead investor firm aiming at laser treatments for ischemic stroke. In terms of your deep dark past, you got your PhD from UCSD in physics, and in fact did postdoctoral work here on ICF. And Mike is currently the CEO of BNZ Energy Incorporated, which described here is a disruptive investment and operating company for the energy transition powered by AI risk management. I just want to say before I give the title of this talk and turn things over to him is we have a fairly flexible schedule today. If people want to come by and talk to Mike, we've changed the room. He will be in building 481, but in room 2117, which is I think that's the old MIT guest office. And then with that, I'll turn this over to Mike, who's going to talk about a physics-based reduced order model capturing the topology of dynamic manifolds. I'll leave it to you.
Okay, thanks very much, Steve. And this work really started probably back in about 2011 when I ended up seeing Stefan Mallat talk first about his deep convolutional transformation called the scattering transform. And that when I saw it initially, I saw a lot of things that started ringing bells in terms of quantum field theory in my mind. He was talking about Vic ordering, path ordering type things in there. There were just also other things ringing in the back of my head with respect to renormalization group too, associated with it. It seemed to have some connection also in my mind to Werner Heisenberg's S matrix and the scattering matrix. And in fact, he called it the scattering transform because I was talking about the S matrix, and even the name ended up coming from some of my early, because I've actually been a collaborator of Stefan Mallat that dates back to probably the early 2000s. And one of the first, we actually deployed Ingo Debauche's proximal gradient methods even before it was published in terms of sparse spike inversion for or deconvolution for seismic data. And I mean, it works spectacularly well as it has in many of the other areas of data science. And but I struggled with this for a decade, and actually over a decade, about trying to understand the relationships. There were different attempts that I made at it, but it just really never hit. But the one thing that I realized along the way was that it was performing extremely well. And that in terms of being able to crack problems that hadn't been cracked before, things in terms of texture recognition, where people were, had very poor, maybe 20% misclassifications, when they ended up using this, taking the logarithm of it, and then using just simple linear discrimination methods, they were getting performances which were state of art of less than 5% misclassification. And so I kept on scratching my head too, associated with that. And then also, I went and had been talking also with John Field, who had been working at this laboratory at the time. And he kept on going and saying, hey, does this have something to do, or in terms of artificial intelligence, with topology, right? And some type of topological type of of analysis. And fortunately, since I've left Sandia National Laboratory and founded this company, and we were in the startup phase of it, that I had the ability to really put up my feet on my front porch, have good morning coffees, and really think profoundly about this stuff. And I never really had that luxury before. And what I'm going to go and present here is that is based off of some work I did under contract with Sandia after I left there. And that I really tried some stuff and it worked spectacularly well in terms of a workflow. And then subsequent to that, and I'll talk a little bit about the scientific exploration method that, I ended up going through, that I ended up going and I think really cracking the nut on this, right? And that it's actually, this is a slide I put together this morning, and that it's not changing actually. Is there a problem with that? Okay. Okay, it's just taking a while to go through. That, this is actually going and is challenging a lot of paradigms, right? And that, I think that even ourselves, we don't realize that things like quantum mechanics actually have gone from a critically developed theory to a matter of paradigm or dogma of where we go and recite things without really thinking critically about it. And here I'm going to be going and taking a look at artificial intelligence. And to think critically about something, I was taught in terms of leadership, executive coaching, that you really need to go and start asking yourselves questions, right? And I want to go, and I don't expect you to answer, right? But as I go through the talk and this exploration is to go and start thinking critically about what we're doing in artificial intelligence, right? And that these were questions that I ended up going and asking myself as I was going and developing this stuff, right? Okay, first of all, what are the variables when we have these nodes in reduced order models, right? Because if you go and take a look at the architectures that tend to be successful, they have bottlenecks, right, in terms of their structure, right? Whether or not that be autoencoders, okay, and I'll be talking about some of those specific structures here, whether or not they be UNet structures, right? Whether or not they be, things like, based off of David Silver's deep reinforcement learning, DQNs, or whether or not they be GPTs, right? These things all have choke points in it, right? Where they're forcing the fit, right, to actually find some type of reduced order model in terms of those limited nodes at the choke points, right? What are those things, right? And in the context of deep reinforcement learning in, Q learning, that if you go and look at the feature value iteration, right, they have these thetas, right, okay? And that, that things are not truly done that way, but you'll go and see what are theta, right, in there, right? And, I was sort of taught in my, grad course on artificial intelligence at Carnegie Mellon that you could choose anything. I don't think there's a statement that could be farther from the truth, right? There are very specific things that you need what those are, and you'll see me go and actually answer this question, right? And then also, if we go and you have all these deep convolutional networks, right? These are functional transformations, right? Going from a function space to a function space, right? From a Hilbert space to a Hilbert space. Well, that's a Banach space, right? We're searching a Banach space, right? Well, that's like impossible, right? Okay. And so what do we have to do? We always make really constraining assumptions about the form of that functional transformation. Even then, we can be left with a billion parameters. So we have regularization techniques to go and further reduce the number of actual independent parameters in the model so that we can fit it with a finite number, maybe 10,000 samples or something of that nature, right? But our brain like comes pre-programmed with this, right? I mean, we don't go and have to do anything, right? It's evolved to have a very particular convolutional network structure, right? So ask yourself the question, why do we spend tens of millions of dollars learning what these structures are on a case-by-case basis, right? Okay. I mean, like our brain just comes that way, right? I mean, I think that you realize, well, we transfer learn a lot. Well, yeah, I mean, you're learning this probably the structure of this deep convolutional network, right? And so, and then an associated question is what is the deep convolutional or functional transformation doing, right? And I really started, those were my introspection questions about what we're doing. It needs to make some sense, right? Now I have the sort of cheeky question, what is Q learning, right? Okay. I mean, that is, what is Q, right? When you're doing deep Q learning, what is the Q function, right? Okay, think about it, right? Okay, and then, John Field's question, right, and which was a real proposal by him, is artificial intelligence related to the topology and geometry of the system's dynamical manifold, right? Are we learning what the homology class is of the topology? Are we learning about what those singularities are, right? Okay. I don't know, maybe. Okay, the next one. Okay, is there a physical justification for rectified linear units, right? I mean, from the early parts of my career, that neural networks were not very successful. Multi-layer perceptrons weren't really successful. The advent of the rectified linear unit was like nirvana was reached, right? When you put those things on there, right? Why? I mean, why? Is there a physical justification for why you're using rectified linear units, right? The next thing is, why is the logarithm so important, right? Okay, that this may not be, I think, but it seems to be you want to throw logarithmic transforms on things to make them work, right? Okay, and it's very explicit in what Stefan Mallat did with the scattering transformation. One thing he actually even buries, and sometimes doesn't even tell you, is he always takes the logarithm of it, right? And in my work that I did based off of Gorgon, I had to take the logarithm before as well as after, right? Okay. And actually, I should have been taking it in between too, but that was a little bit hard to do because Stefan never embedded that in his transformation, right? And like, then everything's linear. Like, what? Huh? Okay. Linear methods work, and they work as well as anything, right? And they have fantastic performance, right? And then also, and this goes to, I don't know, people that have been out there and have had interactions with Bedros Afayem, but he's been talking about stud pulses, right? And he's been doing that, talking about it for quite a while, right? Well, that, go and think a bit, is there an equivalent of ponderomotive stabilization in deep reinforcement learning, right? And is that what Bedros is talking about with respect to stud pulses, right? When I hear him give those talks, I started having a lot of ponderomotive stabilization type thoughts associated with it, right? And can we do something like that, right? And with that said, let me go and jump into my slide of equations, right? And that after this, this is the one slide of equations. I'm going to walk you through just what the steps are, okay, here. But the thing that I'm going to go and want to get and show you in the end, and the magic thing is this recursion relation, okay? And you can see that the recursion relation it's a layer of a convolutional network, okay? In this case, with a set of scaled wavelets, okay? It's a scaled wavelet transformation, where P is the scale of the wavelet transformation. And then it has a activation or a rectifier, okay? And that because this is now going to go and be it's a recursion relation, that you can go up and get to the nth order thing by applying the recursion relation m times. So we end up with a deconvolutional network where the layers are each time that we apply it in the product. So it will have little m layers associated with it, right? Where this actually is what you normally would go and use a ReLU for, okay? But instead, okay, you actually have I, because it's a complex transformation, you have a logarithm, and R naught basically gives you 1 plus x, so that when you take the logarithm of 1 plus x and x is small, that you end up finding that for small x, actually log x equals x. And since we're going to be going and applying this again and again, if we don't have that property, you actually see it blows up, right? Okay. So for convergence reasons, you need to go and have that in there, right? Okay. And so how do we go and get to this formula? Okay. And I will go and talk about the gray box after I get the one to go and relate it to what the normal rectifiers are that we end up using, right? And so let's just start with a normal Taylor expansion of a complex function, okay? And that the Taylor expansion coefficients, okay, are just obviously the derivatives, okay, of whatever that function is. And that this is also, though, I will go and realize these are the S matrix, okay, in terms of what the n particle scattering coefficients are. I will assume that H sub m is actually a functional of the fields and the co-momentums of the fields, okay? I define a convolutional wavelet transform, okay? Here, the standard definition of a wavelet transform. I consider an analytic trajectory, which is parameterized by x. That's nothing more than the convolution, okay, of the wavelet with that. I take the covector along the trajectory by taking d of that. I change the radial coordinates about z naught, which is a little bit of inspiration at this point. So I actually get the property at the end and took a little bit of fiddling, as you may expect. I rotate by pi over 2 to get the covector by multiplying by I. And so I find that dH sub m is equal to d of I log z, okay? And then with this simple definition of what the R naught function is, it's a analytic function, I end up going and getting what the recursion relation is, right? But this is a logarithmic generating function of a complex Hamiltonian, right? And okay, complex Hamiltonian, what? Okay, well, that the real part of the Hamiltonian is the Hamiltonian that we know and love, right? And so you go and you specify that, and what's the imaginary part? Well, you actually don't have any freedom. There is a complex analytic continuation of that of the real part of the Hamiltonian. So you get the complex part as just the natural analytic continuation of it, right? But also that normally, if you go and take a look at quantum field theory, you always deal with respect to exponential generating functionals, right? E to the generator of e to the IH, right? But by taking the logarithm, you actually get a generating function directly of the Hamiltonian. And that's also the reason why the logarithm is being introduced inside of it, right? Okay. And now let me talk a little bit about what this activation function or what the rectifier is here, right? Think a little bit back into your days of complex analysis about what is the complex logarithm, right? Okay. The complex logarithm, the real part of it, is the natural logarithm of the modulus, okay? And that the argument, or the imaginary part of it, is the phase or the argument of the complex number, right? Okay. So that if you now go and first of all take a look at log of R naught, as z goes to 0, okay, it goes to the identity, so we don't have problems. It's a compact mapping, okay, is what that basically says. And then if I now go and take z going to infinity, I actually go and find that it goes to log modulus, right? Well, the scattering transformation has the modulus in it. So if I take log of the scattering transformation, okay, and also take the log of the signal, take the scattering transformation of it, the first order, then take the log of it, I've actually gone to things in this limit, right? Okay. And it actually should be in between every step of the deep convolutional network, just not at the end. But log of log is log. After you do log 2 times, basically, it is.
Can I interrupt with a question? Sorry. Coming from my ignorance. So is what's going on here is we have a set of dynamical variables that we're going to try to use to much more efficiently describe, I think in your case, it's going to be a pulse power thing or something like that. And there's a kind of an equation of motion for that comes from, whatever the original equation was. And so is what you're doing telling us how, so there's a Hamiltonian that evolves that system. There's a Hamilton-Jacobi equation in those funny variables of the partial differential equation, which is my problem. Is what you're describing here or going to be a transformation of the variables in which you describe that system, making it more efficient? I'm putting words in your mouth, but there you go.
Well,
if I got it?
Yes. Okay. But let me just go and I'll give you the answer. You're asking for what the answer is, right? Okay. I mean, right now I'm developing and answering the question of why log, right? Okay. But what's happening, all right, Steve, is that you are going from the field basis, right? Okay. And you're going into a renormalization basis where it's a basis where that each one, you'll find that there are a certain number of spectrums, complex spectrums, right? Okay. And you're decomposing into each one of those complex spectrums, right? And so you're going, and say, if you have a complex spectrum beta of frequency, right, and phase, that now you go into and you project the motion is going to lie on a hyperplane, which is the projection into the renormalization basis, right? So you've gone from motion on a Hilbert space in the deeply convoluted field domain, and you've actually exposed a small number of dynamical P's and Q's by actually projecting onto the solution of the renormalization group equations, right? Okay. And then it becomes a simple matter of finding out what the solutions are to the Hamilton-Jacobi equation, right, in that domain.
So so the original variables and mutations of them come from a, rad hydra or pulse power or some.
They're fields, yeah.
So why is there a Hilbert space here? That's not about.
Because it comes about because you actually have a function of position, right? Fields are something that are defined as a function of positions. They're actually functions, right? Okay. And so that you're actually seeing how functions actually are transformed with time. And so the basic, instead of having a finite number of P's and Q's, right? Okay. You actually have something that's actually a full function, which is an element, it's a continuous function that's an element of a Hilbert space, right? And so that whenever you deal with field equations, you're going and that you are dealing with something that's actually fundamentally an evolution of a function rather than an evolution of a certain number of discrete variables, right?
Well, I mean, yeah, go ahead.
Yeah.
Well, I don't know if you have more questions, but my follow-on question is, okay, so you saw that in some sort of reduced space,
Mm-hmm.
and then there's a mapping from reduced space to the original manifold,
Yeah, that's right. Yeah.
and that is, you're not losing any?
No, I mean, you go and see. Why don't I just go and just finish up showing the relationships to the previous functional transformations that we have. And the next slide is really talking about this, right? And that you can go and also it's really what's going to be developed on the next couple slides, okay? And so let me just go and finish this. And again, I'm going to immediately return to your question, okay, and the like. And that you also can go and show that this is effectively log z times a chirp pulse, okay? And that what Stefan, when he tried to bring in phase into this, ended up going and replacing the chirp pulse with a series of harmonics and decomposing with respect to that, right? He didn't look at it this way, but I'm showing the connection to the rectifier unit, right? And if you only use the leading order term or the k equals 0 harmonic, you end up getting down to just the modulus, which is what he implemented in his scattering transformation, okay? And so now let's go on and really get into what what you were getting at, Steve, and also what you were asking about, right, okay? Is that you go and you're starting here in terms of this basically Banach space of all functionals, right, okay? And this logarithmic generating functional takes you down to the Hilbert space of all possible spectrums, right, okay? And because of the fact that this is a logarithmic generating function, you're going to go and find that you're limited to a fairly low dimensional subspace. And in fact, the dimension of that is going to be 2 times little n, where n is the number of fields, okay, in the problem, or it's going to be basically Cn. So you can do a principal components analysis on this. And you'll see that all of the variation ends up being in a hyperplane that you can find with a principal components analysis, right? And those directions, or those, that it's a set of measures 0, right? For MHD that I'm going to be showing you, little n is 7. There are 7 fields associated with it, right? Okay. And that that when you go and literally find what these principal components are, each one is going to be a complex spectrum. We're going to go and I'll actually show the example of where you actually have 7 complex spectrums, right? And if you went through the normal Wilson procedure and solved for those spectrums, right, you would have now the same spectrums, okay? And so by making the functional transformation and then find the PCA, you find, again, the basis vectors, and those basis vectors are the renormalization group equation. And you can project the original motion in the field domain, okay, into a motion in in the beta domain, which are the projection into those little n principal components that you actually have of the motion, right? Okay. And I think you now realize that the coordinates in, projected into this, which I go and say are the beta coordinates, right, are the reduced order model that, or the first cut at the reduced order model that you're looking at, right? Okay. But now to go and further understand what's happening, right, is that you actually need to go and find a function approximator that needs to go and approximate a analytic function, which is the complex Hamiltonian, right? And this actually goes to the second reason why you like rectified linear units, because this one will now just have a few singularities in it, right? The cohomology classes of it, right? Okay. And I call those the beta stars, or all these beta not Ks, right? Okay, which you can go and also, if you're familiar with Taylor relaxation in stellarators, for instance, that you go and you'll see that you energy minimize, but you actually go down to kind of these ground states, but these ground states end up being the cohomology class, and are actually there's a topological obstruction that you have to go around. You can't go to just sort of zero motion, right? And that, I mean, it's like you had a topology of a torus, right? If you're going around either that you can find that there are a lot of loops if you go around the center or you go around the edge of the donut. You can't go and shrink that trajectory to zero because you're limited by the topological obstruction of the T2 torus, and there are two of them, obviously with respect to the T2 torus associated with it, right? But those end up acting as boundary conditions on any type of analytic function, because if you go and tell me the poles and zeros of the knowing that of an analytic function in the branch cuts, that's a boundary condition. You solve Laplace's equation, and that gives you the analytic function. So that knowing the effectively poles and zeros of branch cuts of a function are equivalent to actually knowing what the analytic function is, right?
So are you saying that kind of makes sense to me? So I have a dynamical system. It's got lots of variables that that obey some complicated equation. You're saying before you take the step of casting it in this description, you have to discover if there's any underlying non-trivial topology. And I guess from my homegrown perspective, would you do that basically by taking loops on the space and then just trying to see what Stokes' theorem says, right? Isn't that what it is?
Yeah, you can go and do that, but also you can map out.
I don't know how often you have to do it, but maybe a lot. But
right, but you also, Steve, can also map out the trajectories, right? Okay, of it, right? And you just have to map out little bits of the trajectories and then go and see how they and find, and by that you can go and reconstruct the analytic Hamiltonian, right? Okay.
So how often is it, or maybe you're going to tell us, in a practical example, that that whoops, you run into a set of variables that have some kind of topological obstruction or something like that you got to fix or drive around or whatever. Is that a common event when you have many variables like that? I would think it might be.
Oh yeah, no, I mean there aren't many of them, right? Okay. And that also, I mean, if you go, and Bedros also has another concept he talks about is bars and stars, right? I even forget now what those acronyms or cheeky things that Bedros always comes up with, but that he goes and he really talks about why do we keep on slightly perturbing trajectories and then integrating them all again in a very hard way, right? If we look at nearby trajectories, that you should be following those nearby trajectories, right? Okay. And what you're looking at here is that if you're trying to map out one of these analytic functions, right, is that, you know, you really can go and easily interpolate them because analytic functions are maximally flat, right? And that's what a solution to Laplace's equation is, right? Except for these few singularities, right? And that's why rectified linear units are so good, because when you combine those into a multi-layer perceptron, you get a piecewise linear function approximator, right? Which is maximally flat, right? Except for places where you have a singularity, which means you have a discontinuity in the first derivative, right? Okay. And that also tells you why sigmoids are like spectacularly bad, because they are infinitely smooth and they can't handle the few singularities that you need. But you don't need many of those tie points, right? You just need to have one of the points beyond the singularity. And it's very easy for a multi-layer perceptron to figure out where to put the cusp. And then they go, and you'll see in my example, it finds where the cusp is, puts the cusp there, and it goes out and is flat as you go away from there, right? Okay. And it also goes and says that these things will extrapolate well, just so you're moving away from a singularity where you've actually sampled it, right? Because it just goes flat. I think John Field talks about this, right? But if for some reason you're starting to get into a part of parameter space where you're walking towards one of these singularities, right? You actually see things are, and you don't have it in your model, you actually see things start getting worse, right? Okay. And that's telling you that there's an additional singularity, and you better go and have start sampling those simulations, right? And it can also tell you that is there actually a beta that's not in your model, right? Are you missing a term in your partial differential equations that you're seeing in the experiment, right? But if you actually went and, let's say, did the experiment and you actually saw there was an additional beta in there that was not actually part of what was coming out of your computer simulations, well, you actually know what beta is. You know the spectrum of it. You know the spectrum of the partial differential operator, so that you know that there is a piece of physics you're missing, and you also know what the spectrum of that partial differential operator are, and that you probably can go and invert back for what the term is. It will give you large clues to what the physics is that you actually don't have or improperly approximating in your simulations, right? Okay. And I think that we all know, as we start scaling up these devices, the paranoia we have we neglected something that's now going to become important in the physics, right? Or is it an extrapolation away from well-known singularities in the function, right? But, going and taking a look at just what these complex Hamiltonians end up being, right, is that you can either map out what that function is, or what the phase space looks like, what the trajectories look like, or actually what the foliation is, or you can actually go and just know what those limited number of singularities are, right? Okay. But also, what's the real problem is that here we have a couple poles and zeros, or a branch cut, okay? And I'll show you an example of that with a simple analytic function, the airfoil function, right? What happens when there is a forward transformation, but also there is an inverse transformation, okay? A well-defined inverse, all right? And so that what you're going to go and understand here is that we're going to go and we're going to do a forward transformation into, okay, this coordinate system, right? And then you're going to want to go and to do predictions or to find out what to apply to the system. If you're controlling it, you're going to want to do the inverse transformation, okay? And I'll actually more specifically show that on some other things, right? Okay. But what you're going to go and see is that we go and we have this convolutional network and we have some bottleneck here, okay? In this case, there's two little n plus one for energy, and I'll talk about that in a second. And then you actually go and expand it back out. And so that's how you go and you see then at this point, this is the reduced order model of the system, right? And I'm just going and showing things in the forward sense, right? Okay. But what we actually get into, and it's what the problem that Ken Wilson had to frontally address with respect to renormalization. What is a very simple pole in this case, when you actually go backwards and go back to the fields, since it's a deep convolution, okay, it basically takes this one pole and spreads it everywhere. And so there are singularities everywhere you look back in the field domain, right? And so what happens in classic renormalization and what that's actually doing is taking all of the singularities and smashing them back together and collecting them in this reduced order model space, right? Okay. You have to be careful that you don't basically throw the baby out in the bathwater, because a lot of times people go and when they go and solve, let's say, the Hamilton-Jacobi equation, everybody loves viscosity solutions. Okay, buyer beware. You're L2 regularizing all of the singularities out, right? They do it because in the fields, you see singularities everywhere you look. You got to get rid of them, right? So let's go and L2 regularize and get rid of all the singularities. Unfortunately, you're getting rid of the one singularity that you want in the process, right? Because you're not being careful about it, right? And so, and it's actually done all over the place in finance, right? It's called interest, right? It is basically resistivity, right? L2 regularization. And they really destroy the economy in the process of actually imposing it physically on the system. Because when the Fed goes and loans you money at a prime rate, they actually are embedding viscosity into the system and fundamentally regularizing the singularities out, and they can destroy the stable points of it, and I'll show you that in a bit, or they can and the like, right? And so now let me go, and also though too, is that what we're really doing is looking at things in terms of extended phase space, right? Okay. And that this Hamiltonian is actually, this complex Hamiltonian is actually operating on the extended phase space. And I'll talk about that a bit more in a bit. But let me go back and take another look at what's happening once we get into these little Q's and P's. I'm gonna have to wait for things to update. So
just forgive one comment here. I don't know how long we have in the room.
Okay.
So I would suggest bringing things to a place also where people may have questions.
Right.
Because again, I don't know. I don't sit over by the laser, but we might be kicked out in 5 minutes.
Okay.
I hope not. But.
Okay. Well, I'll go and skip forward. That's really okay. Okay. Let me go and skip forward to some
physics examples.
Right. And what we actually do is, and this goes back to my PhD thesis, and it's a guiding center motion of an electron in a strong magnetic field. And you can go and actually have a moving ion associated with it. And that what you actually go and want to see here, and let me be rather quick about it in terms of the control theory, is that you end up going and seeing that you actually have, associate the electron, you have the O point and you have an X point, which is a saddle point. These are local minimums, these are local maximums on the saddles. You also, with respect to the ion, have the O point for it, and you also have an X point, okay, sitting out here at infinity, okay? And that you have what are either these guiding center atoms, which are basically an electron bouncing back and forth on a field line and slowly E cross B drifting around, or you actually have both these drifting pairs, which are ions and electrons that basically are both going around their cyclotron motion and drifting each other, and you have free ones, right? Okay. But the thing that you actually want and the point that you'd like to be at, you know, in most cases, are these inverted pendulum, these maximum, local maximum, but they're unstable, right? And that because basically omega equals 0 at this point, and because the mass is equal to 1 over omega squared, if I just go and try to jiggle these things, they don't jiggle if I'm at the point. And the farther I get away from it, because the mass is reduced, they go back and forth more, and I jiggle them more. That causes a ponderomotive stabilization force on this. And that, and also right here, that, I'm sorry, that you probably saw that you can actually stabilize an inverted pendulum by jiggling it up and down, right? Okay, associated with it. And that what I think Bedros is talking about with stud pulses is the fact that you can't just jiggle it anyway. There are going to be, in this case, you know, a few characteristic spectrums, which is a set of measure 0 of however you could jiggle it. And you need to go and jiggle it with those characteristic spectrums, right? Okay. I also went and did a whole large ensemble of Gorgon simulations of MagLIF, and went and did them for different initial temperatures, liner aspect ratios, which is effectively the growth rate of the instability and how aggressive the implosion is, or the growth rate of the Rayleigh-Taylor instability. And because these were 2D in the radial direction, and you end up having vorticity conserved, you actually see an inverse cascade, and these things go and pinch into a dumbbell and then go out, that you don't have the normal regular cascade associated with it, okay? And that, well, you say, well, in 3D, you lose that. No, you don't. You actually have helicity, magnetic helicity, rather than vorticity in 3D. And we actually see you actually go to basically a dumbbell double helix is what it looks like in 3D, where it just rotates around. That I ended up going and doing a large number of these simulations, about 539 on RZ Topaz, that generated about 100,000 images. It took about 200,000 core hours, about 2 weeks, sitting on the machine, the amount they would give me. The training of this workflow, which is what I talked about here, I have a log, I have an MST, I have a log, I have a PCA, and then I have one of these multi-layer perceptrons with 15 layers in the middle of it, right? The training took about 16 GPU hours on my Linux workstation to take the MSTs, and about a day to take the wavelet phase harmonics. But it only took 1 core second to find the principal components and 20 core seconds to train the multi-layer perceptron, right? Because it's a very simple architecture. But then I had a surrogate that actually executed in 1/10 of a core second and simulates what took 360 core hours on the computer to go and simulate, right? And that this goes and shows the the actual simulation versus the generated, both the density and for the magnetic field at 3 different characteristic times, right as the implosion, the initial condition, as the implosion starts, near bang time, and after it's gone and expanded out. You notice that it preserves also the correlation between the 2 fields, as well as many of the details of the simulation. Yeah.
So quick question, really simple. Go back to the picture. So which is the brute force, simulation that is the truth? Is it the one on the left or the right?
Oh, I'm sorry, it's the one on the left.
Okay, so that's the truth.
Yeah, I'm sorry. For some reason, my annotation didn't appear.
So on the right, we're seeing with your method in play, your reduced order model.
That's the reduced order.
Right? Okay.
Yes,
okay.
that is exactly right.
Okay,
yeah. And those are line outs of the 2, so you can actually see, the quantitative similarities, the quantitative.
Right, and then you gave
difference.
numbers for how long it took to do the ground truth simulation versus this sort of slick way of sort of redoing your variables. Okay.
Yeah, and that was 360 core hours to 1/10 of a second.
Okay.
Yeah.
What is the actual implosion? Is it a DDPS or something?
It's a beryllium liner, and the circle is beryllium, and the internal part is DD.
So I guess the question is how well does the reduced order model do on macroscopic quantities like yield and things like that? So
Yeah, we didn't have the physics in there. I was looking at the ability of it to do a surrogate on the field. So yeah. Because and also to go and to understand the fact of what's actually happening, right? Because if you go and take a look at the phi2 component, right, okay, that was associated with the dipole perturbation of the shell, right? You actually go and you see as you actually come in here that the strength of this mode increases, and you obviously see the dipole character of it, right, okay? For the quadrupole character, you actually see a decrease, right? There ends up being an inverse cascade of energy from here to here, okay? And we also are finding in terms of these modes, they actually mean something in terms of physically what's happening. And if I take a look at, how one of these components goes with time, that you go and see now that the actual are the light curves and the simulated are the dark curves, that you see that it finds where the bang time is associated with this. It goes and then fits it linearly, puts one of the tie points on the bang time, and then also does, puts the right number of tie points to follow the curve, right? It goes and finds the one with the largest aspect ratio, the most acceleration, goes and hits, has a shorter bang time. It also goes and shows that as I go to a higher temperature adiabat, it actually doesn't compress as much, right? And then also all the systematics are there. I did a feature importance in terms of prediction of the profiles. Time is the most important, well, of course. The liner aspect ratio matters a lot because that determines the acceleration. The next thing that really matters is the size of the perturbation, but more importantly, the angle of it. Since it's inverse cascading to the m equal 2, it matters what the phase is because it locks onto that and makes it grow, okay? But you go and see then, okay, T naught matters, but not a lot because that only matters at stagnation, okay? Matters how stagnated it gets. But then, phi 4 and 3 don't matter at all. Of course not. Everything's going into there. So you cascade out of it. So it doesn't really matter how much phi 3 and phi 4. But you really see this thing is now inverse cascading, right? But you can actually see that each one of these modes, you know what they are physically. You can make physical interpretations, based on it, and really get insight to the fact that we're getting inverse cascades of self-organization, right? And so if you go back down to Sandia now and say, well, how are you reaching compression ratios of 200 to 1, right? We're self-organizing, right? Yeah, we get growth of the instability, but we actually self-organize into a dumbbell. And so we don't care how much it grows because of the self-organization in it, right? Associated with it. This is actually really controversial, actually, with respect to the fact that we were seeing inverse cascades, right? But I think if you really look at these little tiny, literally we go and compress from, well, they compress at Sandia on the Z machine from about 1 centimeter, and they end up getting 2 perfect helical threads of 20 microns in diameter each. I mean, it's incredible, if you look at, the images that they end up having, right? And so let me just go and get to the conclusions here. And I welcome, there's a lot I didn't have a chance to show you because you were such an engaged audience early on associated with this. But what we really have is a transformational method, right? That's finding these time invariant coordinates, right? That are really the solution to the Hamilton-Jacobi equation, right? Okay. We go from field coordinates to little PQs, but then when you go and solve for that, that H, right, in those trajectories, you end up going and solving for what the solution of the Hamilton-Jacobi equation, which will be big P's, big Q's, and E of P, okay? And also, by the way, what you actually are solving for, and let me go and give you the punchline and the answer to a couple different questions here, right? If I go and take a look at the approximate Q function, right, okay, which is actually normally you go and say that it's a function of little q, little p, and theta, right, okay? That's actually going, and if you looked at it, it's actually going, and it's actually theta of Q and P, okay, in terms of that. That's actually equal to the Hamilton's characteristic function or the action, right? That's a function of Q and cap P, okay? And cap P is actually what you're at is one of the approximation parameters that you're dealing with, right? But this actually is the action, right? Okay, in terms of the solution of the Hamilton-Jacobi equation. Then if you ask, what is the policy, which is little p, right? Okay, that's equal to the partial of W with respect to little q, right? Okay, which is now a function of little q and cap p. That's actually equal to the approximate policy of q and cap p, where this actually normally is just called the approximation parameter, right? And then if I go and find out where the partial of the energy with respect to cap p equals 0, or that's actually the angular frequency associated with it, that will actually give me P is equal to P stars, right? That now I'll go and say that the optimum policy is nothing more than Q of P star, and the optimum value ends up being nothing more than W of Q P star, right? And if you now go and take a look at deep reinforcement learning, right, I've answered a lot of those questions I posed at the beginning, but it's just simply in the context of it, right? And also, you're probably aware of this chasing your tail, lack of independency, lack of stationarity, right? And what was happening was that as you go through the iterations in deep Q learning, you're actually tracing things out and you're converging down to P star. And you're actually, the fact that they're non-stationary is the fact that P is changing as you're actually moving to P star. And all of this replay shenanigans is so that you actually are approximating W of Q of P. And as you're converging in, you're actually tracking out what's actually happening in those cases, right? So that, you know, you go and find that this is, first of all, the reduced order model of artificial intelligence. I think that it's what, if you take a look, I think it's what generative pre-trained transformers or transformations are learning. They're learning this transformation. I just talked a lot about, you know, what's happening in deep reinforcement learning and, you know, in terms of what it's doing here. And I have a lot more detail in the paper. You find out what this decoder encoder is finding. It's a solution to the Hamilton-Jacobi equation. All motion is now geodesic motion, right, on this little PQ space. And that this analytic Hamiltonian is just a solution to Laplace's equation. And then finally, the topology of the low order dimensional manifold is you're doing a topological discovery, right? You saw how this has physical meaning and interpretation. And I talked about very early on the extrapolation and the causal analysis associated with it. Also that for the in terms of the Hamilton, you know, the Heisenberg Scattering Transformation, I've called it that because of its relationship to Heisenberg's S matrix, by the way, right? It's an excellent metric. It exposes this fundamental underlying low dimensional dynamical manifold. But also it goes and finally exposes the fundamental geometrical objects or these relaxed states or the singularities or beta stars. These are the ground states of quantum field theory, the attractive manifold of nonlinear dynamics, the emergent behaviors and self-organizations of complex systems, Taylor relaxed states and BGK modes of plasma physics, the poles and branch cuts of control theory and complex analysis. But really, fundamentally, you're getting at the homology classes of the topology, right? The real fundamental stuff of the topology. And that's actually what's being learned, right? Your brain, at the very core, just goes and finds out what beta stars are, right? And from that, it can inverse reconstruct everything that's happening. It can figure out how to go and control the system, right? About these optimal points, you know. Even you can think about it and you start thinking in psychological context. How do I control my thoughts to stay in a good place, right? You're actually controlling your brain, that complex system of your brain, to stay around one of those X points, right, that you'd like to go and stay at, rather than going down to one of those local minimums or that global minimum of mental depression or mental illness, right? And it actually means this in a big way, not a small way, right, associated with it. I think that there are really profound uses of this in terms of also even the understanding of psychology. And I'm actually working with some psychologists associated with the use of this model. So, you know, there are huge questions, you know, going on, but that's really where I said that, you know, there are a lot of different places where this actually comes in. And in a way, it's a smash up of the learning of this in terms of getting to it, right? And let me just go, and I had one question in the beginning too, in terms of what is Q learning, right? Well, it's learning the action, right? But it's also going and learning that analytic continuation, because the imaginary part of the Hamiltonian is what I would call cap Q in terms of the solution. And that's nothing more than the partial of the W with respect to cap P, right? And that's the imaginary part of the Hamiltonian. And so by finding W, it's actually finding that complex continuation of the Hamiltonian, which are the phase trajectories or the generator function of the canonical transformation that generates the motion, is another way of looking at it. So thanks very much.
Thank you.
Thank our speaker. audience, home and abroad, you might say. I have a question, but I'm going to hold myself back and see if people in the chat or elsewhere, I'm not sure how we can see that here, have any questions.
No, we don't.
Don't have any questions. Okay, looks like a lot of people were on at different times. Yeah, okay, so.
They can unmute if they
Yeah,
have
they
a
can.
question.
Oh, sorry, go ahead.
They can unmute and ask questions.
Okay.
If they want.
So, well, all right, I'll start out with a question then. So I didn't follow everything, but one thing from a big picture viewpoint is the efficiency and also the capturing of kind of dicey topological singularities on this. How much better is it than existing methods, and what kind of problem, let's say you're talking about pulse power, what kind of physics problem could you treat that you couldn't do before? So you gave very impressive numbers for your system versus, I guess a brute force calculation of an imploding liner. It looked like you got these sort of semi-Rayleigh Taylor things about right, and some nice stuff in those pictures. But being a little aggressive about this is, where could you go with this that you could not do before? What kind of problem in physics could you solve that that was impractical previously?
I think that I have that first of all, in terms of performance as machine learning, right? Okay, that not having to go and train the convolutional networks is absolutely huge, right? Obviously, right? I mean, the training becomes trivial, associated with it, right? And that, tens of millions of dollars taking up, it's really tough for DeepMind with AlphaFold, et cetera. I mean, they're really burning large amounts of computer time associated with that, right? Okay. Other things in terms of causal analysis, right? It goes and gives a framework, right, where you can actually, well, first of all, it gives high fidelity surrogates that go and conserve all the proper quantities, right? And when I say high fidelity, that you conserve those quantities that actually go to the right emergent behaviors, right? Okay. And don't have the issues of wandering so far away from the physics or having effectively numerical dissipations and the like eventually eat your lunch, okay, long term, no matter how high order the methods are, right? And that's absolutely central to being able to have any type of Bayesian analysis, right, or post-Bayesian analysis. You need a very fast surrogate associated with it. You need the 10th of a second surrogate to be able to go and do that type of analysis. So it goes and will go and enable that, right? But also, though, too, is that, I think you have to go and say, supporting causal analysis is huge, because it can go and start knowing when your data is whispering at you that there's going to be trouble when you scale up your experiments, right? And you have ways of hypothesis testing of, are we getting some new physics? And if we actually brought in that new physics and actually ran it again with the new physics, scaled up, you'll start realizing that some physics we've been neglecting is eating your lunch, right? Okay. So you can, and I think, and it's an overall, I think, challenge. I don't think that the current methods don't support the causal analysis, right? Because you don't know what you're getting, you don't know what these variables are in the like, right? And you can't go and do those hypothesis testing of, do I have all of the right directions, and are those directions in the right direction, right, associated with it, right? And I would be much more positive with respect to these singularities, right? I mean, that, they aren't like, painful, they aren't painful annoyances. They are the answer, right? Okay. So that, it's not that there's something that allows you to get around. No, it's something that you actually, that is the answer that you want to get to. I mean, it's like Hitchhiker's Guide to the Galaxy. Well, I can tell you the answer, but you aren't going to like it, right? It's beta star, right, is what the answer is. So the singularities are everything. And, you know, and also in terms of renormalization just itself, that, you know, this is not, you know, where you have to, you know, have, you know, divine inspiration of how to collect all the singularities. This actually is a prescriptive way of you do it and it collects the singularities for you, right? So I think in terms of even analytic renormalization of field theories, that it will, on the analytic side, give you a way to go and get the solution to the renormalization group equation, right? And also, I think,
Hi, Mike.
sort of point, it's much more
This
profound
is
to be able to, I think it has real implications about finally unifying gravity with the other, you know, field theories that we have, right? Because I mean, I think that Murray Gell-Mann, you know, obviously in his life's work really went in terms of the quantization of the particles and fields of SU1, 2, and 3, really went and had all those things. But it actually will go, and in the thinking that I've had, I think this has a real ability to bring gravity into the fold and put it on a common ground with the quantizations that we actually have in terms of SU1, 2, and 3, right? Which is the E&M weak and strong forces, for instance, right? You know, the electron positrons, you know, the normal baryons and the quarks, you know.
may I have a question?
Yeah, sure.
Oh, hi, Mike. This is Milan. Can you hear me?
It's who?
Oh, that's
Milan Holak.
Okay.
So the question is, it seems like we are trying to find a balance between stability and accuracy. And so usually we would work with entropy. It's like a good measure. And so in your framework, could you comment on the sense of entropy when defining the topology of your manifold? If it's like meaningful, can you put like a number? Okay, this manifold, this entropy, and so to keep the singularities, but keep the dimension low as well.
That, I mean, the one thing to go and note about this, and I'm going to take it on board in terms of the exact mapping to the part of entropy, but the thing that you are looking at here as it goes and interacts with the external systems, those are the actual thermal forces that, you know, I was going and looking at, and that there is a, and I'd have to go and I mean, again, I really have to think about that. That's a very good question. And let me really think. I can't say offhand, and I haven't really thought of where is entropy and what I'm talking about.
Okay, thanks. I will shoot you an email.
Okay, that'd be really good if you could, yeah. Send me an email and I will respond.
Awesome, thanks.
Well, I don't have a question, but I have a comment. You know, in the perspective of reduced order model, a lot of people just apply the PCA, like so-called the POD, proposed order.
Yeah.
When you do that, you don't get the great compression, like compressed solution representation. When you apply that to advection dominated problems or, you know, transport problem, but a lot of, you know, magnetic hydrodynamics, you know, they are driven by transport.
Yeah.
So, you know, people recently, they started to add a neural network The reason being is there's a nonlinear activation functions you can actually, map in nonlinear fashions so that you don't have to rely on the linear compression only. But I see your work at the PCA component and also HST, which involves with the logarithmic transformations with the Hamiltonian, and then later on layer MLP, which also has a rectified LU, the activation function. I do see that you have all the components, what we do usually to form a reducible model. So, but in addition to that, training is a lot cheaper than the usual neural network training, right?
Right.
So I totally agree that that's great advantage. I myself wanted to apply this to.
Yeah,
We
no,
just saw the technology
I think
we
that you've
Me
gone
too.
and said it well. I mean, if you go and take a look at what is here, you can go and see how what's here is reflected in what's happened, what you've ended up, what works, right? Okay. And you can see mappings of this and the structures and the like, and say, yeah, this is, I see where this is happening, but it's like, but there are no things to fit, basically, right? Other than the PCA, right, associated with it, which is a trivial operation, right, in the end. And that you're right, that they realized it didn't work, right? If you're working in the field domain, yeah, you see the huge HST here in order to be able to get it into the domain where it is linear, right, okay? But then it's only linear, you're confined to this hyperplane, right, okay? And so it's linear with respect to the fact you're confined to a linear subspace, but it's far from linear in that subspace, right? It has a very, rich topology, in that subspace. But it's not so, but in the end though, it's not that rich, right? I mean, there are only a few singularities in that subspace that determine the whole thing around it, right? Okay. And so that, in terms of where you normally go in the convolutional networks, right, we're all trying to get down to where the space where it is linear, okay? And that they actually will go and get it to a space where it's not linear, but it's curved, right, okay? And then they'll use an MLP to actually snap it to linear, right? Okay, and then, but by construction, they're kind of, they don't need to do the PCA anymore, right? Because they have that nonlinear mapping, right? So the convolutional parts of it are just getting it so it's there, but a bit curved, and then they have to go and snap it. But if you've done it correctly, it's already linear, so you can just use a PCA without having to have an MLP at the end of it, right? Okay. But then once you're in that space and get the projection into that reduced order model space, that there's another thing of finding out what the Hamiltonian is, right? Because you need to know what the trajectories are. And that an MLP is great for that because, it's single value, it goes and wasn't single value, but it just has a couple branch cuts and singularities. And, an MLP eats that stuff up, right, associated with it. So you're right, it has those different, the character of the stuff in there. But, because I know it's a solution to the Hamilton-Jacobi equation, right, okay? And it has the form of that, and I didn't, have the time to show this, right, is that I can actually structure a web of MLPs with specific number of nodes where I know exactly what that node is going to be, right? If I looked at it, that is what those things are, right? One is the action, the WQ of the cap P. The other one is E sub P, right? The other ones are the cap P's. Another one are the big Q's, right? Okay. And so that you now have gone and further constrained the network, right, to actually match the solution form of the Hamilton-Jacobi equation, right? But there were cheap ways of doing this because and that's what I did here, because if I know this has 15 nodes, then I just have PQ. I have some layers in between, right? And I just know I need to have 15 things here, right? Okay. So this is kind of, I don't know what's what. They could be admixtures of each other, right? But when I look at this structure, there's no doubt about what things are. And so you program this into TensorFlow or, or PyTorch, and you can actually play these nodes out, and those are P, right? Okay. Associated with it, right? And so there's much more intelligent design into what this Hamilton-Jacobi equation solver is really what this is. And you know trivially what the propagator is, right, in it. Or you can also know what the force is in this, and then you transform back out. And those were things I didn't show, right? This is how you use this in terms of a surrogate, right? Oh, shoot. I have to do stuff to force it here. Is that you start with initial conditions, you apply the HST PCA, and you get the initial conditions in terms of this. You have an MLP that actually goes and gives you the P naught Q naughts, right? I now have a Hamilton-Jacobi solver, which gives me cap P's Q naughts, right? I now have a propagator, which I know trivially, okay? And then I get big Q's. I go and have the inverse, which gives me little p's, little q's. I have an MLP that gives me the output function in P and Q. Then I have the inverse transform that actually gives me the output fields, right, that I end up having, right? And so that, now you have the Lego block, right, okay, associated with it. And you have a very well-constrained Hamilton-Jacobi equation, and this has absolutely nothing to learn, where normally you're spending $100 million to train that thing, right, associated with it. So, and then, if I have a controller, I just go and have the Ponder motive force here. Then I just go and give this, and I'll tell you what the force I need to apply the system in order to stabilize it, right? So
let me suggest this, Sumit. If there are any last minute questions, this would be a good time to ask them. Otherwise, we're going to migrate up to your home away from home upstairs. And so that's to remind people if they want to drop by, that's building 481, room 2117, not the one in the earlier messages, because the door was locked. So, but upstairs, it should be good. And, look forward to
right.
it.
And, again, I mean, if I encourage you to come by and talk to me,
Right.
And the person with the entropy question, I think it'd be great if you stop by and we could actually discuss it and maybe do some research real time. It'd be fun.
So let's, I've got to, fortunately, go.
Okay,
So,
but
I want to make sure
thanks.
I want to make sure you get upstairs. So,
Okay.
Thank
Yeah.
you. Thank you, everyone.
so I guess we log out. Very good.
Okay. Thanks for your, this is very different, but you guys were so engaged.